We are doing thermal remediation methods. My name is Carter Black.
I'm Joe Sullivan.
I don't want you to say that.
I'm the consultant.
Kyle.
Okay, Courtney Mann.
Just as an overview of what we're going to go over today, we're going to first be looking at the physical mechanisms. The way we're going to split it up is we're going to talk about several different thermal remediation methods. The physical mechanisms are going to explain just how the method works. It's going to go into depth about how the heated, how they're removed, and all of that. The next thing we're going to look at is the influencing factors, such as the size, the area that we need to treat. We're also going to look at factors such as what type of contaminant it is and just how that influences what we're going to do. The next thing we're going to look at is instances of field implementation. So that's going to be how the method was employed in the field. So we're going to look at some case studies and how successful they were and whether or not the remediation method actually worked in that situation. The next is going to be demonstration level. That's also going to be looking at some different case studies and seeing just how well it works. The applicability and limitations are once again going to look at the influencing factors just to make sure that the situation where we're employing the tactic is suitable and that we're actually going to have a successful remediation plan for that situation. And the final thing we're going to look at is cost and availability. We're going to make sure that we list out the prices. We're going to compare the prices at the end of the project just to make sure that we have a good grasp on what is going to be appropriate to use in what situation. So thermal remediation refers to the in-situ application of heat and energy injection to heat and mobilize the contaminants in the subsurface, either in soils or in groundwater. The general goal is to recover that material using some methods, and each one of the methods that we're going to look at is going to employ different methods to actually accomplish that goal. So these are going to be the strategies that we're going to look at today. The first is going to be electrical resistance heating. The next is going to be incineration, followed by plasma pulse technology. Then we're going to do thermal desorption, and followed by smoldering remediation and steam injection. We're going to get really into depth with all of those, so I hope you're ready.
So the first one that we're going to look at is called the electrical resistance heating. So for introduction, usually it's used to heat contaminated soil to a high enough temperature to increase the volatility of the contaminants. Energy is then applied through electrodes into the ground while passing alternating current through the soil and water. And that may induce the groundwater to boil and then create steam. So this is just an example of a 6-phase layout. There's 2 different kinds that have been used. There's a 6-phase or a 3-phase. The advantage of the 6-phase is there's a more even distribution of heat. So for the physical mechanisms, there's a few that we have to look at. Electricity is supplied from a nearby source and then applied to the electrodes. As the temperature increases, the soil heats the contaminant and the groundwater. Heating the vapors increases vapor flow and vapor pressure, promoting vapor displacement. Most DNAPL components will partition into the vapor phase and be able to be removed through vapor extraction. For the influencing factors, there's some on the contaminant side and the aquifer side. So for on the contaminant side, it's used to remove PCE, TCE, and most chlorinated solvent DNAPLs. However, the compounds with lower volatility will not be treated as effectively. On the aquifer side, rocks are generally non-conductive, so most current will flow through soil and groundwater. The current decreases as the soil dries, which decreases the conductivity. It is well suited for fine-grained soils with high soil moisture content, but vapor transport may limit the contaminant extraction. For field implementation, it's generally simple. The electrodes are placed 8 to 20 feet apart for 3-phase heating. For 6-phase heating, it's in a hexagon shape with a diameter of 17 to 40 feet. The electricity is applied and the resistance to the current flow between electrodes heats and boils some of the groundwater, which generally takes about 2 weeks to reach a boiling temperature. The steam that is generated from the boiling groundwater carries the volatilized contaminants to the recovery wells, and then the vapor is recovered at the surface. ERH has been most widely used to treat VOCs like TCE, PCE, and methylene chloride. So for the demonstration level, one company that I found that has experience with ERH is called the TRS Group. They have successfully remediated over 130 sites in the US and some overseas. One of their sites was a TCE remediation in a deep bedrock in eastern PA near Philadelphia. The 20 feet of overburden was mainly medium to fine grained sand and clay. They used the ERH for the first time in a very thick rock unit of 90 feet, which was primarily sandstone, siltstone, and some thin seams of coal. The site was an active manufacturing facility that used chlorinated solvents as degreasers in the production process. The focus of the remediation zone was adjacent to the plant building with the goal to remove an estimated of 483 pounds of TCE. The highest reported concentration of TCE was 560 milligrams per kilogram near the degreaser. They installed 17 vertical electrodes with co-located vapor recovery wells and 3 temperature monitoring points spaced at 5-foot depth intervals. This is just a picture of the remediation zone, and they estimated that applying 1.6 million kilowatt hours of energy over a 70-day to 90-day period would remove the estimated mass. The consultant who represented the property owner performed routine sampling of recovered vapors using a photoionization detector and a collection of vapor samples for lab analysis. So this is the results of the lab analysis and the vapor steam sampling. So this helped them decide when they had to cease the operation since they knew it went down enough. The system removed 399 pounds of the chlorinated solvents, and they operated until they reached the 1.6 million kilowatt hours, which took 82 days. The samples collected from the 2 monitoring wells within the treatment zone before and after showed a 99% reduction of the TCE. And here is a YouTube video illustrating an example of their method.
This animation illustrates in situ thermal remediation of chlorinated volatile organic compounds in soil and dolomite bedrock using TRS electrical resistance heating. 4 contaminant source areas partially below buildings were remediated in 2009. The results of one of the source areas are in this animation. The red mass represents the contaminant. The vertical black rods are the ERH electrodes that were co-located with recovery wells. The electrodes deliver energy to the subsurface and convey steam and vapors to the surface for treatment. The electrodes do not get any hotter than the surrounding soil. The days of operations and contaminant mass removed are in the upper left and right corners of the animation screen. Subsurface temperature increases slightly faster in the areas of highest contaminant concentrations. This is advantageous because these areas clean up quicker and can be turned off early following sample confirmation. The remaining energy is redirected into the areas until they are cleaned up also. This eliminates wasted energy and saves time and money. Average subsurface temperatures increased at a rate of 1.5 degrees Celsius per day during heat up, and the maximum subsurface temperature reached was 114 degrees C. At the end of ERH, final contaminant concentrations were orders of magnitude lower than the guaranteed remedial goal. Confirmatory soil sampling included independent analysis of 204 soil samples collected from 71 sample locations. Over the 6-month ERH operating period, 600 pounds of contaminant mass were recovered. The contaminant mass was reduced by 98.4%.
So for the applicability and limitations for this process, the applicability is the current decreases as the soil dries, which decreases the conductivity, making it well suited for fine-grained soils with a high soil moisture content, but the vapor transport may still limit the contaminant extraction. It's generally a short treatment time, taking 9 to 18 months total, and it's commonly applied under buildings or manufacturing facilities. Some limitations, there is the heating remediations do not recover the contaminants, so they must be coupled with another system for full contaminant recovery. The level of cleanup depends on the types of contaminant present at the site, but soil shrinkage should be considered under certain geological conditions. For cost and availability, I found a few different companies that offer ERH as a remediation technique. The TerraTherm pricing was at $70 per cubic yard for a large and deep CVOC site, but it can increase or decrease depending on the size of the site. US EPA in 2004 had estimated $32 per cubic yard and $73 per cubic yard at 2 full-scale sites, while Bike and Fleming in 2005 had estimated a total cost around $200,000 plus $40 to $70 per cubic yard. And next I'm going to hand it off to Nick for incineration.
Thank you. So incineration is a process which volatilizes pollutants rapidly and completely. Failing to do so through incomplete combustion has the potential to produce nitrogen dioxides and sulfur dioxides, which will be discussed further on in the limitation section, but is presented here as a visual. The two forms of incineration which will be discussed are rotary kiln and circulation bed incineration. Before incineration can take place, the soil must be physically removed and transported to the incinerator. Large rocks and debris must also be ground up and water removed. One strong influencing factor of whether or not incineration is implemented is the solubility of the contaminant itself. Incineration is most useful for contaminants such as PCB, which has a very poor solubility as we dealt with in class, and will likely have a much smaller range as opposed to a contaminant such as TCE, which could occupy a site larger than what would be economically feasible for incineration. Another influencing factor would be the boiling temperature of the compounds which the contaminant breaks into. Contaminants such as petroleum products break down into harmless compounds with higher boiling temperatures that can be returned to the site. An example of incineration used in the field would be the Bard and McGuire Superfund site in Holbrook, Massachusetts. Between 1995 and 1997, incineration was used to remediate the soil of pesticides and disinfectants that contained dioxin and volatile organic compounds. The form of incineration used was the rotary kiln incineration. A brief overview of the process would begin with the soil being trucked to the incinerator, being combusted, passed through a hydrostatic scrubber, and combusted a second time. Finally, all the ash from the approximately 100,000 cubic yards was returned to the site. Another in-field example was at the Barrow Bonfuca Superfund site in Slidell, Louisiana from 1993 to 1995. Incineration was used to address polynuclear aromatic hydrocarbons and benzoapyrene. The form of incineration used was again a rotary kiln. Again, the soil was trucked to the incinerator, combusted, and the gases were passed through a hydrostatic scrubber and combusted a second time. The ash was once again returned to the site, making sure that it met a standard of 10 milligrams per kilogram of polynuclear aromatic hydrocarbons. So two types of incinerators include the circulating bed combustor, which relies on high-velocity air particles to keep the solids suspended as if they were in a fluid. This maximizes the surface area exposed and provides an even temperature gradient across the particles, which allows them to undergo complete combustion. The second would be the rotary kiln combustion, which rotates around like a giant fiery composter to expose all of the particles evenly to the heat. Shown here is a circulating bed incinerator in the combustion. I'm moving the mouse. In the combustion, I lost my place. In the combustion bed, my sincerest apologies. In the combustion chamber, particles are held in a fluid-like state and are eventually passed on to the cyclone. In the cyclone, the denser particles fall through to be re-incinerated or passed on as waste through the bottom, while flue gas is passed on above to another chamber to either be re-incinerated or go through other processes. In rotary kiln combustion, the solids are mixed in the combustion chamber, while the gas is separated and combusted again in the secondary combustion chamber. Incineration has several drawbacks, one of which is permitting, as you can only have one incinerator for PCB or dioxin disposal sites. A second drawback is the potential contaminants that can be produced if incinerated improperly. Nitrogen oxides and sulfur oxides can be produced, which are an irritant and health risk especially to those who have asthma. Heavy metals can produce bottom ash and volatilize, which could potentially require extra installations and be more costly. Again, dangerous VOCs pose a risk to individuals with asthma. Finally, sodium and potassium residue can attack brick lining in the nearby buildings. Finally, the cost of incineration. Going back to the two previously mentioned sites, the Bard and McGuire site cost approximately $133 million and came out to be about $650 per ton of soil. And finally, the Baru site cost approximately $72 million to remediate and came out to an approximate price of $440 per ton of soil. And now we will go on to plasma pulse technology.
So I'm going to be talking about this technology. So this is more specifically branched from enhanced oil recovery as a remediation method. This technology manipulates electronically generated plasma vibrations by reducing viscosity, increasing permeability, and improving the flow of other contaminants to the surface. This is conducted in situ and post in operations such as fracking. This is for mostly oil specifically, and these hydrocarbon chain molecules underground are broken down with these plasma pulse vibrations so that they can flow through smaller openings as opposed to creating larger fractures. So performed on a horizontal scale, this method is far more effective than a tertiary or a secondary refracking or acid treatment operation. I'll talk more about this in the cost and availability section, but this operation is much cheaper, especially on a horizontal scale, as opposed to refracking because there's no water, there are no chemicals, and the energy needed to treat the fracking fluid or the acid is also negligible. This apparatus, on a vertical scale and a horizontal one as well, generates hydraulic impulse waves as fast as the speed of sound, which opens the perforation zones, clears clogged sediment, and alters the chemical structure of these hydrocarbon molecules. Nanofractures are also created, and the effects added up ultimately increase the permeability of the oil or desired contaminant. As an influencing factor, this technology is new in the industry. It's recent within the past decade, meaning that this hasn't been used very widely and it is more effective on a smaller scale. It's also more effective for secondary remediation and has been mainly used, like I said, for oil extraction and oil recovery. This method is also safe. It has treated hundreds of wells with absolutely no incidents, and this operation is also fast, such that this is done in a matter of hours, and the well goes back into production almost immediately. So, as I said, this technology can reach previously untapped oil reserves using a cleaner and cheaper method. This initiates resonance and plasma waves within an oil reservoir and then enables the oil to move with greater fluidity through smaller fractures in the earth. And as I said already, it works on a smaller scale, such that this tool can be used by at least 2 workers and it can be moved by hand. The power source is also small compared to general fracking methods because high energy capacitors are stored inside the tool. This is important to note because this eliminates the need for big rigs, sand trucks, pumping trucks, such that there is a limited amount, like aka smaller, of equipment used and people on the site's location. From a demonstration level and from an outside perspective as well, the apparatus looks simple, but it's actually fairly complex. What you need to operate this apparatus with is a wireline truck and a laptop computer. So that part is very simple, but there are sections to this apparatus that basically perform different operations, and I have a video on the next slide which will go more in depth and show a cross-sectional visual.
Welcome to Novus Energy. At the present time, the ability to recover existing reserves is one of the most pressing tasks facing oil-producing companies in the world. This is because it is well known that all primary and secondary production methods have allowed for only a 25 to 50% recovery of the underground resources. This has left more than 50% of all hydrocarbons still in place in identified reservoirs. Novus Energy USA was founded to help in the enhancement of oil recovery, utilizing our patented method and device. We believe this will allow for the world's proven reserves to be extended indefinitely.
Here we have the basic features and physical properties inherent to all wells within a reservoir system. The geological structure of rocks forming a reservoir is not uniform. The remaining oil in place is concentrated in zones with poor draining. According to its acoustic properties, a reservoir is an array of vibrating systems. We have ascertained that a periodic pulse influence on the layer system can result in a parametric resonance in it. Well building is accompanied by formation of the drainage area, the condition of which has a substantial impact on a well's productivity, both at the development stage and throughout the entire period of the well's operation. The basic factors determining the permeability or mobility index in the drainage area, which are common for all wells, are the following. Clogging of the well by solid particles present in the liquids used for opening the well and subsequent completion. Clogging of the drilling mud. Clogging of the well by salts and paraffins. Novus has developed a downhole tool which is able to clear the drainage area and increase the permeability of the reservoir at the same time.
The treatment starts by lowering a measuring device into the well to determine the following hydrostatic parameters: pressure, temperature, liquid flowing level, and the determination of the working perforation interface. After collecting the data, the plasma pulse generator is lowered into position at the prescribed depth to match the perforations. The control module on surface is used to generate a series of plasma pulses, which take milliseconds to eliminate clogging within the drainage area and deliver a compression wave resulting in a rise in temperature in the plasma channel. Sedimentation is pressed into the formation, and when the plasma cools down, it's forced back into the well by the reservoir pressure. The wave-created forms of broadband acoustics into chromium and transfers into the liquids media of the reservoir. The latter ones fade out rather slowly, and because of that, their amplitudes increase with subsequent pulses, resulting in resonance events. The following effects can be observed: multiple increase of liquid aggregation, Flotation of oil drops are forced to the surface. Due to action of the elastic wave, new fissures appear in the rocks of the reservoir. Permeability enhances, and the porous space changes, and oil displaces water. The elastic waves also reach the neighboring wells, enhancing the filtering properties of the entire reservoir. Upon completion of the treatment, the generator is taken from the well, and the well is put back into production immediately. The Novus plasma pulse technology has now been proven in over 200 wells to economically increase oil production and
So I thought that was fairly interesting. Anyways, moving on. This method, as the video said, differs from traditional fracking, and the hydrocarbon chain's ability to adhere from the rock is changed. It's more applicable because, as I mentioned earlier, it doesn't cause acidization. There are no chemicals used, and the energy requirements of this technology are minuscule compared to fracking because these pulses, like the video said, last for a nanosecond. I guess I'll go into more depth about these shock waves. So this emits a high-power shock wave that produces a non-linear broadband, repetitive, pulsing and directed energy characteristic. And these shock waves propagate and translate into elastic waves in this reservoir. For these elastic vibrations, in natural heterogeneous reservoirs, they produce plasma wave frequencies that increase the mobility of the crude oil to the water. And what's also nice is that after this operation is completed, the mobility of the oil can continue or the increased and enhanced mobility of the oil can last for up to 12 months post this well treatment. And as far as limitations go, there aren't many. It isn't widely used, and I guess it's more common to use on a smaller scale operation as opposed to a larger one. This slide just is taken from Jardine Oil from a case study, and it just shows that after the plasma pulse technology treatment, the increase in barrels of oil per day increased by 98% and by 127%, and this was performed in Hayesville, Kansas. So as far as costing and availability goes, on a vertical well, this technology is 75% cheaper than an equivalent hydrofracturing job, and on a horizontal well, depending on the lateral length of the project, it can be up to 90% cheaper. Cost differentials are extremely influential when determining these methods of extraction in an industry that especially favors environmentally safe methods, as well as when there are slumps in oil prices. Also, as a major cost, a cost that is negligible after this technology is performed is that service companies injecting acid into wells, into the perforations to melt away the buildup and restore the water pressure, charge about $25,000 to $35,000 per cleaning treatment. And as I said, this is a cost that won't be needed with this operation. The average drilling operation per foot for a fracking operation is $245 to $143 and fluctuates accordingly in response to the commodity at the current time. And what I just looked up recently was that there are 42 gallons of oil per barrel, and the current price is $68 per barrel of oil. And we can do some math and figure out that that comes out to $1.62 per gallon. And this method doesn't necessarily cost as much as a fracking operation, but the amount of oil that is that you're able to enhance and recover is, like I said, 90%, 100%, some were even 200% more efficient, and you're going to make more of a profit because you're going to be able to extract more. And like I said, this is important because this method is an oil enhanced recovery, and you'll be able to extract more. And we're going to move on to thermal desorption next.
Awesome. So me and Joe are going to go over thermal desorption. So thermal desorption, so it removes organic contaminants from soil, sludge, and sediment with the use of heat. This method is different than incineration because this method requires heat to physically separate the contaminants instead of actually destroying them, which is what Nick talked about earlier. So regarding physical mechanisms, there's 3 types of ways that you can apply the heat. So there's direct fired, indirect fired, and indirect heated. So direct fired, as it sounds, you're applying the heat directly to the contaminants. Indirect fired is essentially the direct fired rotor dryer heaters, or their air steam is applied to it instead of the fire. And then indirect heated is which externally fired rotary dryer volatilizes the water and organics from the contaminated materials. So there's 2 types of thermal distortion designs. There's rotary dryers and then the thermal screw. So the rotary dryers is a horizontal cylinder that can be indirect or directly fired, while the thermal screw has a screw conveyor that can only be indirectly fired. So, thank you. So some of the influencing factors are listed here. So chemical and physical characteristics of the waste material, geotechnical properties of soil being treated, design characteristics of the thermal desorption systems, and the system processes operating parameters. So these are mainly what companies look at when they're deciding if this is the right method to go about remediation. So this is just an overview of how this process goes about. So as you can tell, there's 2 steps. So the first step is you heat the material to volatilize the organic compounds, and then after that happens, essentially you're condensing it into a vapor. So this is what makes it different from an incineration process. So essentially after the off-gas treatment is applied, it separates into either releasing into the atmosphere or residuals. And so then the other diagram just shows this process, but more with the thermal desorber, which is in the center, which that's where the heat is applied to.
Alright, now we're going to move on to a real-world application which was done at the Industrial Latex Superfund site in New Jersey. There, a high-temperature thermal desorption was used to clean up contaminated soil. From 1951 to 1983, manufactured rubbers and adhesives contaminated soil with SVOCs, PCBs, and arsenic. And then from April 99 to June 2000, over 53,000 cubic yards of contaminated materials were treated, or were excavated at depths of up to 14 feet. During the process, 225 tons of contaminated soils were treated every day, and they actually had to be treated by thermal absorption 2 times before they backfilled the site. Now for some general applicability for this process. It's proven effective in treating organic contaminated materials, including fuels, pesticides, and both semi-volatile and volatile organic compounds. It has versatile treatment methods because of its ability to be implemented on-site or off-site. For instance, larger projects you would probably want to do on-site to cut down on transportation costs, and smaller sites, there's no reason to build an entire thermal absorption unit on-site, or on-site, so you would just transport those small quantities. And then there's always going to be limitations. So for example, specific particle sizes and materials, or specific particle size and materials handling requirements that can impact applicability or cost at specific areas. Sometimes dewatering might be necessary if there's high moisture content in the soil. And also, highly abrasive feed material can also damage a processing unit. And then finally, heavy materials in feed can produce a treated solid residue that requires stabilization. And this is just going over some costs and availability. This whole chart is a breakdown of the size and difficulty in respect to which contaminant you're treating. And then we have over here two key cost drivers. The first one being economy of scale, which just talks about the quantity of materials that you're treating, and also moisture content, which I just mentioned. More moisture content would require more heat input, which is concurrent with fuel costs.
So next, I'll introduce the smothering remediation. The smothering remediation is a thermal technology for treating the non-aqueous phase liquids, and it's such like the air is forced through the material to be treated to propagate a low temperature flameless of the combustion. And it can be used to treat the wide range of the non-aqueous phase liquids, including the coal tar, the crude oil sludge, and other difficult to treat materials. And it can also be used for ex situ treatment for the excavated soils and the sludges, and in situ above and below the water table. Thank you. And the physical mechanisms is like, firstly, the heat and air applied to the small portion of the contaminated soil until the ignition temperature are reached. And secondly, the smothering reaction initiates. The heater is no longer needed and is turned off. And the air injection continues, and the burning non-aqueous phase liquid is converted primarily to the carbon dioxide, water, and also heat. And the heat is absorbed by the adjacent soil, and the non-aqueous phase liquid allows the process to continue. The reaction will continue propagating in the direction of the airflow until the pathway doesn't contain the non-aqueous phase liquid anymore, or until the airflow rate falls below a critical amount required to support the reaction, which means we can end the reaction by ourselves. Thank you. And the chemical mechanism is like, the smothering is a flameless type of the combustion. The reaction occurs within the surface of the fuel. It's activated by raising the contaminants to its ignition temperature and ensuring the presence of the oxygen. The reaction is an exothermic oxidation reaction. It happens like the carbon compounds and the oxygen together to produce the carbon dioxide, water, and energy. Energy generated is more than the energy used to heat the fuel and lost externally. So the smothering remediation is also called the self-sustaining reaction. And the influencing factor of the smothering remediation are firstly the porosity of fuel or fuel embedded matrix, because the reaction requires air to flow to and then diffuse into the fuel surface. Secondly, the air injection rate also matters, because the propagation rate is linearly dependent on the rate that the air is injected, which means the velocity of the mass destruction is easily contributed by manipulating the air injection rate. Thirdly, the non-aqueous phase liquid type matters, because the temperature of the reaction zone depends primarily on the non-aqueous phase liquid type, typically ranging from the 500 degrees C to the 1000 degrees C. And last but not least, the compound volatility matters, because if the material is too volatile like the gasoline, it may be difficult to ignite. So then we need other like non-toxic fuel to support the smothering, which means we cannot use the direct smothering. And The smoldering remediation is most readily applied to the long-chain hydrocarbons, such as the coal tar, fuel oils, and unrefined or heavy petroleum hydrocarbons, with non-aqueous phase liquids contain significant embedded energy. An ideal tons per hour range in order to sustain a smoldering reaction has been estimated at 31.2 to 104 grams per kilograms for the crude oil and 28.4 to 142 grams per kilogram for the coal tar. Thank you. The first type of field implementation for the smoldering remediation is the in situ smoldering. It's usually used in a pilot test. And this is the video from the equipment typical pilot test stages. And you can see that to the ignition point and some heat and air is like put air injected. And this reaction is happening below the water table. After the heat is transferred through the contaminants, the temperature rises. And then the combustion begins, with the air continually injected. Now the heat is turned off and the reaction can go itself to propagating through the every direction with the contaminants present. And this is a photo show that how the soil is different between and before and after the remediation. You can see that for the before soil it has like the black color, the contamination, but after the remediation the black part is all removed. Oh, thank you. And the second type of the field implementation is the ex situ smoldering. The ex situ smoldering is relatively straightforward because the issue associated with the heterogeneity and airflow distribution and the vapor management are more easily controlled and optimized. The smoldering material can either be the excavated, contaminated soil and organic liquids from lagoon or industrial process that are mixed intentionally with sand. The technology was shown to be equally or more effective at larger scales. And this photo is a smoldering remediation at full-scale site treatment at a formal chemical manufacturing facility in the United States. And the smoldering remediation is typically used as a source treatment technology where the goal is the non-aqueous phase liquid destruction or to the extent practicable. And it can be applied for both low volatile material and high volatile material. Typically used for low volatile material such as the coal tar and the petroleum hydrocarbons, because for low volatile material we don't need other supplements. And then the suitability for the site for smoldering treatment could easily be determined by the laboratory treatability study, and the process can tolerate some site heterogeneity. It can also be applied both above and below the water table, just like the video shows the smoldering is below the water table. And actually, the smoldering remediation below the water table is really common. And it's appropriate for soil contaminated with both light non-aqueous phase liquids and dense non-aqueous phase liquids. But just like I mentioned before, the smoldering remediation is not appropriate for remediating materials with low air permeability and requires a minimum amount of non-aqueous phase liquid to propagate the self-sustained reaction. And the smoldering remediation has the self-sustaining manner for many days in all directions, represents with a major advantage in terms of cost saving, carbon footprint, and life cycle assessment. And the costs were estimated at 260 to 330 per metric ton. As smoldering remediation has rapidly evolved from a new idea to technology being commercially applied to contaminated soil, both ex situ and in situ.
Okay, the last part is the steam injection. During the thermal recovery, the reservoir is heated to reduce oil viscosity. Thermal enhanced oil recovery is the most popular method, according for more than 50% of the overall enhanced oil recovery market. Steam injection is the most common method used in thermal enhanced oil recovery. Other methods include in situ combustion, where the reservoir is heated and an injection high oxygen gas mixture burns to create a combustion front. Steam injection is mostly used in shallow reservoirs that contains high viscosity crude oil. The injection of the steam lets heat the crude oil in the formation, thus lowering its viscosity and vaporizing some of the oil to increase its mobility. And this graph shows the viscosity and the crude oil caloric value relative to the steam injection. And the steam injection enhanced oil recovery contains two distinct categories. The first is the cyclic steam stimulation, and the second is the steam flooding. In cyclic steam stimulation, the same well is used for steam injection and oil production. At first, steam is injected for a period from couple of weeks to couple of months. The introduced steam allows to heat up the oil immediately surround the injection well through the convective heating, thus lowering viscosity. This two graph is the cyclic steam stimulation and how does it work. After the target viscosity is reached, steam injection stops to a low heat to redistribute evenly in the formation. This helps maximize the amount of the recovery after this stage. The well can then be produced until the temperature in the well drops and the viscosity of the increase again. After that, a new circle of the steam injection starts to heat up the recovery. And this graph is steam flooding. In steam flooding, injection and production wells differ from each other. There are two wells. Steam is introduced to the injection well and is driven toward oil to physically displace it, while heating it to reduce viscosity. Steam flows require continuity in the formation to allow steam to drive oil toward the production well. And we have a 1 minute video to show how that will work.
Our engineers are using horizontal steam injection to safely and cost-effectively increase recovery from new and existing reservoirs. First, we drill wells down hundreds of feet before turning the bit horizontally to drill out thousands of feet in the targeted production zone. Once the well is complete, an injection well pumps steam into the reservoir. As the injected steam makes contact with oil, heat is transferred to the cold heavy oil, reducing its viscosity and making it flow more easily to the producer well. This approach efficiently recovers more resources with a smaller environmental footprint than drilling multiple vertical injection wells. It also enables Chevron to develop thin reservoirs, lower costs by eliminating the need for multiple vertical wells, and increases oil response with higher injection rates.
Steam flooding is a process used by Chevron to increase recovery from heavy oil reservoirs.
And for the influence factors, the injection of the steam lets heat the crude oil in the formation, thus lowering its viscosity and vaporizing some of the oil to increase its mobility. The decreased viscosity helps reduce the surface tension, increase the permeability of oil, and improve the reservoir seepage conditions. Oil vaporization allows oil to flow more freely through the reservoir and to form better oil once it has contact.
So I will share a real-world case. The Canadian natural resources, they use the increased circulated steam or half and pump technologies to develop bitumen resources. This technology requires one well boom and the production constant of injection and production phases. The first steam is injected for several weeks, mobilizing cold bitumen. Then the flow on the injection well is reserved, producing oil through the same injection well. The injection and production phases together comprise one circle. So steam is re-injected to begin a new cycle when oil production rates fall below a critical point due to the cooling of the reservoir. Applications and limitations. Steam injection is usually more economic friendly compared to other EOR methods. Therefore, fewer complications arise when it's used. The steam itself does not pose a great threat since it is just condensed water, which cause no pollution. And steam injections can sometimes severely damage underground wells in structures. This happens in reservoirs which are prone to geological rearrangement. The performance can endanger the lives of the workers and damage to the equipment. Therefore, steam injections cannot be used in the type of reservoirs unless extra cautions is taken. Moreover, steam injection can be a technically effective recovery method for carbonate reservoirs. Within certain parameter ranges, this method usually helps recover a large portion of oil, and in some fields where combinability is favored, both methods can be implemented. Cyclic stimulation followed by steam flow. Cost and availability. So while steam cools in the well, it turns into water, which mixes with oil. This added extra operations cost since larger volume of liquids must be handled. Furthermore, an extra dehydrated facility is needed in nearby to allow for adequate separation of oil and water before oil settles. And economic challenge is one of the determining factors in using steam flow. Steam flow is more costly than circulated steam, since it requires more steam to be used during the process. When steam injections begins for the first time, 1 barrel of steam inject can recover up to 30 barrels of inthermal oils. After some time, the efficiency of the process drops and 1 barrel of steam is only about to recover 0.2 barrels of inthermal oils. And at this time, the process becomes uneconomic. Since steam price rises up to 30 per barrel of inthermal oil recovers, and if natural gas is used for steam generation, And under those conditions, production will shut the weld until the oil price raise or another temperature is implemented. And this
So in order to kind of quantify all of the different methods that we've had on a comparable scale, we decided to plot the cost per ton of soil treated by the method. As you can see, incineration has a very wide range of prices. That's mostly due to the conditions at the site and the limitations that are going to be placed on that method. If you have a certain type of soil, it may be much more expensive to incinerate it. You might have to do it multiple times, and that drives up the cost. The next most expensive method is going to be steam injection. That again varies quite widely. Again, it's going to be based on the limitations of the actual site. And you're doing it in situ in that case, so again, your prices are going to be increased for that reason. Next, we have thermal desorption. It's between $60 and $180 per ton. Again, the range is getting smaller as we go down, but again, all of these prices are going to be basically limited by the applicability and the types of soil and contaminants that are going to be at the site. Smolder remediation and ERH are relatively small ranges because they have a certain applicability that they have to be used for, and they may not be able to be used outside of that. You may notice that Kyle's plasma pulse technology is not on this chart. The reason for that is it's more of a secondary treatment, and we couldn't really quantify it by dollars per ton of soil treated. Even with that, regardless of what you think of the video that Kyle showed you, I think it's a pretty interesting technology, and I think it was worthwhile to talk about. And with that, that is the end of our presentation, and if you have any questions, we will do our best to answer them.
Okay, thank you. As the man says, any questions? All right. No? No questions? Did you see in situ soil vitrification as one of the techniques? It's already in the notes, right? But exotic.
We tried to pick some that we thought were interesting. There's several more that we didn't really go into, but there are several
What
other
were
ones.
they?
Well, as you said, that one. But yeah.
No problem. So you realise a couple of your things are ex situ
Yeah.
incineration and plasma pulse is a completions method for shale gas and tight oil wells, I think, not so much for remediation. Do you know if it's ever been used for remediation?
Well, I mean, post-fracking it, for the definition of thermal remediation was just, like the energy aspect of it besides like the heat injection, so.
Well, a lot of these methods for cleaning up sites are developed for enhanced oil recovery. So steam injection certainly is used, and what the Chevron movie you showed is that, but it's also, there's lots of applications, as you mentioned, for that in shallow, non-indurated soil reservoirs, etc. So I don't know whether it is actually used for that, but it certainly could be.
I branched it off of the enhanced oil recovery concept. I thought it was interesting, so I wanted to find as much as I
Okay.
could about
No
it.
problem. Does anyone have a question yet? No? Right. Thank you.
Thank you.
All right, well, that's it. For those of you who came in later, you should sign the sheet. I mentioned about the grades. The grades will be online, plus your 3% or 2% or 1%. Do you like the way I introduced that to you? Give you the 3% to come first. I'm sure we've got a good yield of people coming to the presentation. And that's it. SRTs are open, I guess, till Friday. If you want to leave some comments, you should. It's always interesting to read them, see what's going on.